For me, and I think for most of us, sunlight is it's the source of everything. It feels like the ultimate giver of energy for life.
Right. It's what we're taught from day one,
Yeah.
photosynthesis.
Exactly. But what if there are entire worlds, thriving miles under the ocean in just total darkness where the sun is completely irrelevant?
Well, it might sound like science fiction, but it's very real. It's just pure chemistry.
So that's what we're getting into today.
Yes. We are doing a deep dive into chemoautotrophs. These are organisms that have, well, completely bypassed the need for light. They're tapping directly into geological power.
And our mission here is to figure out how this works and, I guess, why it matters, why understanding this is so important.
It's crucial not just for biology, but for future technology as well.
Okay, so let's break this down. I hear these terms thrown around a bit. Chemoautotrophs, chemoheterotrophs. Where do we draw the line?
The line really is all about primary production. So both groups are what we call chemotrophs. They get their energy from chemical reactions, specifically oxidizing inorganic molecules. Think iron or sulfur.
So they're both using chemistry for fuel.
Exactly. But the chemotroph is the ecosystem builder. They capture that chemical energy and they pull carbon dioxide from their environment to build, all their own organic parts.
So they're literally the primary producers. They're taking rock and CO2 and just making food.
That's it.
Like a solar panel, but it's powered by some kind of subterranean battery.
That's a great way to put it. Instead of using light to split water, like a plant, they use the energy released when chemicals react. Say when hydrogen sulfide meets oxygen, they're sort of rusting their way to energy.
And the chemoheterotroph.
The chemoheterotroph also uses chemical energy, but it has to eat. It has to consume carbon that something else already made. It's a consumer in that dark world.
And these places, these self-sustaining ecosystems, they're in the most extreme environments on the planet.
Oh, absolutely. The poster child is, of course, the deep-sea hydrothermal vent.
Right.
Vents are just these incredible chemical factories. The pressures, the temperatures, they completely shatter our old ideas of where life can exist.
Yeah.
We find these hyperthermophilic.
Meaning super heat-loving.
Exactly. Superheat-loving chemoautotrophs. I mean, take M. candleri. It's a methanogen that survives at 122 degrees Celsius.
122 degrees, that's well above boiling.
And at 20 megapascals of pressure, it just uses CO2 and hydrogen to live.
How does a cell even hold itself together at that temperature? I mean, shouldn't its DNA just unravel?
Well, that's the big mystery we're still working on. We see incredibly stable enzymes, specialized cell membranes. What's so fascinating, though, is that these particular organisms, the ones using rock and minerals, are the nexus of the whole system.
The nexus.
Yeah, they're converting geothermal energy heat from the Earth's core directly into biomass, into life. And that supports entire communities miles above, all in absolute darkness. Thinking about complex systems like this, where these, hidden agents can unlock such a massive impact, it really forces a new perspective on things.
Speaking of complex systems, this deep dive is sponsored by Embersilk. If you need help with AI training, automation, or software development, or if you're trying to uncover where intelligent agents could make the most impact for your business, you should check out embersilk.com for all your advanced AI needs.
Okay, but the fact that these microbes can survive at 122 degrees, that's just wild. Does that extreme robustness have any practical use for us up here on the surface?
Oh, absolutely. That resilience is key. They have some really surprising applications, especially in things like sustainability and resource recovery.
Right, like the bioremediation and bioleaching.
Yeah.
We use a chemoautotroph called Acidithiobacillus ferroxidans. It loves to oxidize iron and sulfur.
Bioleaching. So you're basically using microbes to mine for you.
Precisely. We use them to dissolve and extract valuable heavy metals. We're talking copper, nickel, even uranium from low-grade ores or industrial waste.
Which has to be cleaner than traditional methods.
It's much cleaner and more economical than high-heat smelting. And that thermal stability you mentioned, that's why other extremophiles became so vital in our labs.
Of course. The thermostable Taq polymerase for PCR tests.
Exactly.
The enzyme at the very core of all that pandemic-era testing came directly from a heat-loving microbe. It's a direct line from extreme biology to breakthrough medicine.
It is. What's important to remember, though, is that even with all this, there are still huge gaps in our knowledge of these deep-sea ecosystems. We still can't say for sure what the actual rates of carbon production are down there.
And we don't know who all the main players are.
We don't. We haven't fully identified all the dominant microbes driving these cycles.
So, wrapping this up, Considering these organisms thrive on pure chemical energy, miles underground, with zero reliance on the sun, does that change your definition of where life might be possible elsewhere in the universe?
Oh, absolutely. It pushes the boundaries every day.
It makes you think that any rocky planet or moon with an internal heat source could be just teeming with life, even if its surface looks totally frozen and dead.
It's one of the most exciting questions in astrobiology right now.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.